Hi, in this video I would like to point out the differences as far as memory complexity is concerned between breadth-first search and depth-first search. So for example, we have a tree-like graph like this. The root node is the 1, we have several leaf nodes, the 8, 9, 10 and so on, and basically we would like to compare the breadth-first search and the depth-first search as far as memory complexity is concerned. So let's suppose that we are dealing with breadth-first search. We start at the beginning and then we are going to visit the neighbors of this given node, then the neighbors of the neighbors, then the neighbors of the neighbors and the neighbors and so on. So basically we visit all the nodes on a one-by-one basis, in this case in a sequential order. Okay, so the 9, then the 10 and the 11, then the 12 and the 13 and 14 and 15. So what does it mean? That we have to store a lot of references in a queue abstract data type, as we have discussed earlier. And the question is, okay, how many items do we have to store in the queue on average? And if we have n items stored in the balanced tree, in this situation we store 15 items, then there will be n divided by 2 leaf nodes. So we have to store ordo n items if we want to traverse a tree that contains n items. Basically this ordo is the upper bound, and basically the leaf nodes are the bottleneck. So when we are dealing with the leaf nodes, this is the situation when we have to store the most items in the queue abstract data type. And that's why the memory complexity for using queue is ordo n. So for example, if we have 100 items in a balanced tree-like structure, then the memory complexity, so how many items do we have to store on the memory with the help of the queue, it's going to be ordo n, so ordo 100. Okay, so let's consider depth-first search on the same graph. We start at the root node, then we go as far as possible on the left subtree, so we visit the 2. Then we came to the conclusion that it has a left child again, so the 4. And the 4 has again a left child, the 8. But the 8 doesn't have any left child. Basically, it doesn't have any children. So here, this is the situation when we have to backtrack. Depth-first search, if we come to the conclusion, it is a leaf node, so there are no children at all, then we have to backtrack, basically go back to the previous node. And that's the situation when we pop item from the stack. So basically we just have to store as many items on the stack as the height of the tree. And basically it is the logarithm of the number of items we store in the balanced tree. So if we store 100 items, then the height will be logarithm 100, and basically the memory complexity will be ordo log n. And that's why depth-first search is preferred when we just have to traverse the tree-like structure or the given graph. Then depth-first search is going to be memory friendly in the sense that we have to store ordo log n items on the memory instead of the ordo n. And basically, just to summarize again, that if we continue the depth-first search on this given graph, then it's going to be the 9, then the 5, then the 10, then we backtrack again and visit the right child of 5, then we visit the right child of 1, then we visit 6, 12, 13, 7, 14 and 15 in the end. So just to summarize again, the memory complexity was the difference between breadth-first search and depth-first search. For breadth-first search it is ordo n. For depth-first search it is logarithm n, and because logarithm n is smaller than n, that's why depth-first search is preferred most of the times. Okay, it's very important that there may be some situations where breadth-first search is preferred. For example, several artificial intelligence related algorithms concerning, for example, robot movements, breadth-first search is preferred. Why? Because breadth-first search is going to discover the local environment, because it goes layer by layer. Depth first search, on the other hand, is going to go as far as possible from the given point, and that's why for a robot movement it's not going to be feasible. So sometimes breadth first search is preferred, sometimes depth first search, but we have to know that depth first search has an average better memory complexity with ortho n. Okay, thanks for watching.